How does snow melt and become water that's available to infiltrate into the ground and supply streams and plants? Well, let's first consider a typical temperature profile within the snowpack. So going down here, we'll have depth. This will be the ground. And then on this axis up here, we'll have temperature. And we'll put here the freezing or melting point, so 0 degrees. I guess we don't need the degree. And then maybe down here we'll do -10. So in the winter, it tends to be a profile something like this, where it's warmest at the base of the snowpack and it's coldest at the top of the snowpack. And the reason this is that the air temperature is rather cold and there is a geothermal heat flux that's coming from the ground that tends to warm up the bottom of the snowpack. And so you see some profile like this. This is a winter profile of snow temperature. And there's another thing that may happen is that this may be a nighttime profile. You may, in the daytime, see some departure where the top of the snowpack warms up during the day and then it cools off again at night. And so you have this kind of swinging temperature arm up here at the top of the profile. This is nighttime. So this is the typical winter temperature. Let's say this is maybe December. To get snow to melt, though, we need to bring it up to the melting point. And to get what is called an isothermal snowpack, where the whole thing is one temperature, and only then can we really begin to melt significant quantities of snow. And so maybe this is spring, or depending on where you are, summer temperature profile within the snowpack. Okay, so this is what it looks like in terms of temperature. There's 3 basic steps to accomplish snow melt. And the first phase is known as the warming phase. And in this warming phase, we are trying to get the temperature of the snow from something less than 0 degrees Celsius to an isothermal snowpack. To describe the amount of energy that's required to bring this snowpack to the melting point, we use a term called the cold content. And so we're going to do an energy balance for this whole problem and think about how much energy is required for each step in snowmelt. The cold content is defined as the amount of energy required to raise the average temperature of the snowpack to the melting point. So, to define it mathematically, we're going to say that the cold content, Q sub Cc, which will have units of joules per square meter, so this is the amount of energy per area, looking down from above at the snowpack, is going to equal the following: negative C sub I, which is the specific heat capacity of ice, rho sub W, the density of liquid water, the snow water equivalent, and then finally the temperature, the average temperature of the snowpack minus the average temperature, the average melting temperature. So if we're using SI units, this is going to be 0 degrees C. So let's do a quick analysis. This is the heat capacity of the ice, sorry. This has dimensions of joules per kilogram degrees C, or per Kelvin. The density of liquid water is going to have units of kilogram per cubic meter. Snow water equivalent is, remember, the height of the liquid water column if all the snow were to melt. And then this term here is going to be in degrees C. And so the kilograms cancel out, the degrees C cancel out, and we're left with joules per square meter. And so this is indeed the amount of energy that's required to bring this snowpack from whatever its average temperature is to an isothermal condition where it's at the melting point. This is just to bring it to the melting point. This isn't the amount of energy that's actually required to melt any of it, which we will talk about in the next videos.